Let's start by reading the caption to this photo here. In the past, observations of boulders and glaciers had to be pieced together to understand the landscape. Today, we have access to high-tech information. This image of the Swiss Alps taken from the space shuttle shows peaks alternating with valleys carved out by glaciers. So if I put this in present mode here, you can take a look at the photo and see those valleys. Looks pretty cool. All right, I'm going to get out of present mode. While it is impossible to know what the weather was like at any particular place and time before humans started making and recording such observations, we can deduct what the climate was like by using fossils, ice sheets, trees, and corals. By observing these indicators, scientists have concluded that Earth's climate has changed many times during its history. The scientific community has sought the reasons for climate changes and identified 4 important factors in climate change: volcanic eruptions, variation in Earth's orbital patterns, solar output, and greenhouse gas levels. All of them are rooted in a single idea. Climate change is a matter of energy in versus energy out. Earth gets most of its energy from one thing, the sun. If Earth takes in more energy than it sends back out to space, Earth warms. If it sends out more than it takes in, Earth cools. So let's read about volcanic eruptions reflecting or trapping solar radiation. While Benjamin Franklin did correctly surmise that volcano eruptions can cool Earth, he did not quite get the whole picture. Volcanic eruptions both warm and cool Earth, but their cooling effect is stronger than their warming effect. The warming effect comes from the release of both human-caused and nature sources of greenhouse gases into the atmosphere. Carbon dioxide, water vapor, and methane are released during volcanic eruptions, and they trap heat that radiates from Earth's surface. The cooling, on the other hand, comes from the tons of rock and ash particles and liquid droplets and gases that volcanoes spew into the air. In particular, sulfuric acid in the atmosphere reflects and scatters the sun's radiation, acting like a shield against solar radiation and bouncing some of it back into space. When volcanoes blast sulfur-rich gases into the air, the sulfur reacts with vapor, and the result is clouds of sulfuric acid. This is why the 1982 eruption of Mexican volcano El Chichón has much stronger effect on global temperatures than the enormous explosion of Mount Helens in 1980. El Chichón, though it blew less rock and debris into the air than Mount Helens, pumped out more sulfur-rich gases. This caused global temperatures to fall up to 5 times as much as they did after the Mount Helens explosion. It is important to understand that volcanic eruptions happen all the time on Earth. Whether or not they affect climate has to do with how extreme the eruptions are. After very large eruptions like Tambora, the Indonesian eruption of 1815, or Krakatoa, a volcanic island that exploded in 1883. Earth may cool by a degree or more over a year. Let's go back up to this photo here, and the caption reads, "Volcanic haze east of the summit in the Kailua volcano caused by the release of gases." Moving on to variations in Earth's orbital patterns. The planet comes close to the fire and warms itself come near to the fire, and you feel warmth quickly. Move away and feel how fast you get cold. Our main source of energy is the sun, so another way for Earth to change temperature is to change how far it is from the sun. This was a theory developed by Serbian astrophysicist Milutin Malinkovic. He noticed that Earth changes its distance from the sun in 3 ways. First, the Earth's orbit is not a perfect circle, so it's not always at the same distance from the sun. As its farthest position from the sun, Earth is about 5 million kilometers, or about 3 million miles, farther away than the sun as its nearest position. Furthermore, the shape of the orbit, or eccentricity, changes. Over a span of about 100,000 years, Earth's orbit goes back from being nearly circular to slightly oval and back again. The more elliptical or oval the orbit, the greater the difference between the Earth's maximum and minimum distance from the sun. I'm going to put this slide back into present mode. Oh, actually, I apologize. You're not going to be able to see it. But if you put your own slideshow into present mode and you can look closer at that photo, the shape of the Earth's orbit or eccentricity changes over the 100,000-year cycle. So the orbits in the diagram are not drawn to scale, but it is an example of how the orbit is changing. Second, Earth's tilt on its axis, or obliquity, changes, swinging back and forth in a 40,000-year cycle, like the sunbather sitting up in a lounge chair and adjusting to lean back. The change in the tilt is not huge, about 3 degrees, but is enough to change how directly the southern and northern latitudes face the sun, and that changes the amount of solar radiation they receive. The more directly we face the sun, the more solar radiation we get and the warmer we are. So again, another photo example of here is how the tilt on the Earth changes its axis by a few degrees over that 40,000-year cycle. And finally, as Earth rotates on its axis, it wobbles like a gyroscope and it spins. It does this very slowly in about a 22,000-year cycle. Without this precession, you would expect that we get closest to the sun in the same season every year. However, because precession makes Earth gyrate, sometimes the planet makes it closest approach to the sun during winter in the northern hemisphere, and sometimes it comes nearest when winter is in the southern hemisphere. Right now, Earth comes nearest the sun during winter in the northern hemisphere, which makes winters relatively mild. But 11,000 years ago, Earth came near the sun in July, making northern summers very hot and northern winters very cold. By charting 3 types of Earth's motion, Milankovitch calculated that changes in solar energy reaching Earth over the last 600,000 years and matched them to changes in the Earth's climate. For about 50 years, his theory was ignored, but in the 1970s, it was rediscovered by the climatology community and embraced. When Earth's motion around the sun gives us severe winters in the north, ice and snow build up on the landscapes and persist through the summers, and we have an ice age. We are due for another ice age in 50,000 to 100,000 years. And then here again is another photo example of the precession or changing of the orientation on the Earth's axis over that 22,000-year cycle. I'm going to go